Hey guys, so I'm back and I will be continuing on with the lesson steadfastly. There's not a ton left to do, so it shouldn't be too bad, but we're going to go through some more theorems, really talk a little bit more about some properties. So our next theorem is about multiplying with the identity matrix. So the basic thing that you need to understand is that when you have a linear transformation with the identity matrix on either side, that leaves it unchanged. So, in other words, if you have A here equals that's just going to equal A. Because, the identity matrix is really just going to multiply out to equal the original matrix that you had. That's kind of the point of the identity matrix. So that is really straightforward. That should not have been a big shock or anything, but I just wanted to point it out, throw it out there. But the next thing we're going to talk about is matrix multiplication being associative. So a reminder is that while commutative is like switching numbers around, associative is grouping numbers together. So we're going to have the same thing where we've got A being an n times p matrix and B being a p times q matrix. We're also going to have C being a Q times M matrix. So we want to find the relationship between A times B times C and A times B times C. So we can sort of prove this because we can say that AB times C is really going to equal AB times the vectors of C, the column vectors of C, that is. So if we write out the column vectors of C, that will give us these V's all the way up to vector M. Well, if we multiply these things, we obviously know that that's going to become AB times V1, and then AB times V2, all the way out to AB times the vector M. But then if we do the same thing, but where we've got this second thing going on, what we end up with at the end, if we go through the same process, is A times B V A B V2, and so on and so forth, right? Well, we know that these two have to equal each other. We know that this form is equal to this form because we already talked about it. We already proved before that AB times a vector is the same thing as A times B times a vector. In the former case, we were using X, but here it's the same principle. So that proves that these matrix compositions and matrix products are associative. So we can say confidently that AB times C equals A of B times C. And there's also like a conceptual way that we can prove this that is very, very similar. I'm not going to go through it, but there is a cool drawing that I think can be helpful. So if we've got R in the M, R, or the space Q, the space P, and the space N, I will remind you that in this case, we've got A being N times P, B being P times Q, and C being Q times M, right? So knowing all of this, we can say some things. So first we can start out by saying that from here to here is AB. From P to, not P to M. Sorry. From N to M should be BC. Sorry, that was incorrect again. BC should be from here to here. From here all the way to here is A times BC. But then we can also say from here to here is AB times C, because those two are the same. So I'll color code these. These two are equal to each other, right? But then sort of the components, if we break it down, we've got from here to here and from here to here. I really like this diagram. I like how it shows the movement to the different subspaces of R. And I think it's really, really helpful. But the main thing to take away is that matrix products are in fact associative. You can group them around and they are still the same. They're just not commutative. Which was, I think, a good crash course in returning back to some of those terms from like pre-algebra. But yes. So the next thing that I want to talk to us about is the idea of block matrices. There's also a theorem about the distributive property of matrices, except for I've used that many times throughout this lesson, and I think we get it. You can distribute matrices and they still work. Sometimes I think the proofs in this book go a little above and beyond in, you know, repeating each other a little bit of rehash. Okay. But we're going to talk about the idea of a block matrix, a block or a partitioned matrix. I'm going to write that out in big letters so we don't forget it. A block / a partition. Okay. So this is when we have a matrix that is something like this. 1, 2, 4, 5. 6, 7, 9, 3, 6. And in this case, we would break it down into 4 components that we would treat as 4 entries on their own. we would just treat them as 4 simple entries. We would write this out as B11, B12, B21, and B22. So from here, what would we do with that? Well, the basic idea is that if it's true that we're going to treat these like matrices, if we're going to figure out how, so basically if we want to figure out the ijth entry, we just return to what we said before, where we used the dot product idea when we were multiplying matrices, and we treat these like just normal entries of matrices. So we would have A1 or AI1 times B1J plus AI2 times B2J, all the way on, so on and so forth. You could also condense this down into another sigma sum. But let's look at how this would actually work in action, because this is probably a little confusing to visualize if you don't actually do it. I know it was hard for me until I looked at the example. So it's really quite annoying that you can't just erase this whole board. Well, you'd be surprised at how difficult it is to find a good whiteboard and like screen recording device. I'm not going to say it's the hardest thing I've done so far as part of this independent study, because it's not, but it was frustrating. So if we've got an example where we've got something like 0, 1, 1, 0, and then negative 1, 1 times 1, 2, 4, 5, 7, 8, 3, 6, 9. Right. So we're going to pretend, basically what we're pretending here is that these are just 4 components. So that means that and this is 2 components. So that means that this would be times this, and then times that. So we would have 0, 1, 1, 0 times 1, 2, 3, 4. And because it's the dot product, we would of course add. What we would add would be negative 1, 1 times 7, 8. And then on the bottom, we would have 0, 1, 1, 0 times 3, 6 plus negative 1, 1 times 9. Now, that would be how you would go about multiplying all of this out. And then you would, actually multiply all of these things. You would multiply the components times the components and see what you got. One question that I do have going into next week is that, like, if we look at this one right here, you can't actually multiply that, right? Because, it doesn't add up. You just can't multiply those 2 things based on what we already know. So I'd be curious, does that sort of nullify the existence of this whole thing, or just that part? How does that really work? The book didn't really specify. But the very last thing that I want to finish with today is this idea of the power of transition matrices. And power in like the literal sense, like raising something to an exponent, not the strength. So we're going to return to the website example and in fact, I don't think we ever did the website example. So we're going to go back to an old lesson and I'm going to explain how it works. And we're going to sort of bring it into focus with this new lesson. Okay, so if you've got a website and you've got these different pages, here, let me just draw the diagram first and then I'll explain how it works. Okay, so you've got a website, you've got 4 different pages. You've got page 1, 2, 3, and 4. You've got people who are waiting to take the first link that they find, and you see where they end up. You see the distribution matrix. So the way that you would do this is you've got like, these are the places that the people can go. For example, if you start on page 2, you could click either over onto page 1 or onto page 3. So you can write out the systems of equations where you've got y1, y2, y3, and y4 corresponding to the 4 pages you can end up at. And you set that equal to 0, 1/2, 0, 0, 1/2, 0, 0, 1. This is very messy. 1/2, 1/2, 0, 0, 0, 0, 1, 0. This is insanely messy, not super helpful. But the basic idea here is that we've got these x1, like this would be x1, 2, 3, and 4. So for example, if we look here, to get onto page 1, like if you ended up onto page 1 after clicking over, that would mean 1/2 of people from so 1/2 of people from x2 are able to go to page 1. Sorry, this should be a down arrow, right? Because this is the column for x2 and this is the row for y1. So the only people who can end up on y1 is 1/2 of the people from the 2 page, right? And from there, they really talk about the idea of distribution matrices, which is where you can sort of move everything, over. You solve down for, you solve down to the RREF, and then you can find sort of an equilibrium distribution. And what an equilibrium distribution is basically the idea, you've got an initial distribution and then the distribution such that A times vector X equals vector X. So to figure that out is what we would basically say is you want to have a distribution vector, and the idea of a distribution vector is it all has to equal up to 1. So what I mean by that is, say our initial distribution of where people were on these pages was, there was this 0.4, 0.1, 0.3, and 0.2. Right? This all equals up to 1, right? Like to distribute something, it's distributing the whole into different parts, the whole being 1, and distributing it into these different parts that are going to these different pages. So when you figure out the equilibrium distribution where A times X equals X, what you basically do there is that, so you say that you figure out like x1, x2, x3, and x4, what those are all equal to, and then you figure out, you would multiply x, basically you would put x1, x2, x3, and x4 in terms of some other variable t, and you would figure out what t would equal, and you would do that by adding up x1, x2, x3, x4 equals 4t, so making t 1/4, and you would multiply 1/4 times what you got for x1, x2, x3, and x4, and that's how you get to an equilibrium distribution. So I'm doing a horrible job of explaining that, mainly because it doesn't really matter for the purposes of what I'm trying to do. Basically, what you need to understand is that we've got a website. We're trying to figure out, we've got a website, and we've got, I'm going to keep this little thing right here going on because this is actually useful, but all this stuff can go away. What we want to figure out is, so basically we want to be figuring out, if we iterate the process, the equilibrium distribution, in other words, the sort of the limit that you might say, where, you know, you're continually getting this number. You keep iterating the process and you continue getting this same number. We see this when we use iterations in things like exponential equations. We see that we get sort of an equilibrium distribution where it eventually evens out. This is like just a general phenomenon. If you've done biology, you know that this happens with population. You just kind of even out to a certain point where it's like, no matter how many iterations you do, you end up at the same number. And we're trying to find that number. But a way that you can do that is, so we've got this transition matrix right here, right? That I've already sort of explained to us. So basically what you can do is you can raise this matrix to different powers, A2, A10, AM. And one important thing to note here is that you have to use your calculator for this. You can't just multiply every individual component by itself. It doesn't work. That's just not how the process works. You have to use technology. You have to use a calculator. If you're really curious and you have the level of engagement that you actually want to try this, which is very doubtful. If you're watching this video, you're probably glancing at it and being like, oh, that looks cool. But if you did happen to be possessed with such a desire to figure out how to do this, you like look on the internet, find a brief explanation of how to use your calculator. It does not work to do it on your own. But the point is that if you kept going, you would eventually reach an equilibrium distribution. And in fact, it's really another way of figuring out what I tried to very poorly explain in the last example, because I was, explaining using distribution, finding the equilibrium distribution, but without this idea of raising it to powers. But this is another way that you can find the equilibrium distribution, because if you keep raising it and raising it and raising it, eventually you will keep getting the same numbers or close to the same numbers over and over and over with each new iteration, and you will realize that you've reached the limit, basically. So I'm going to give you my last little bit of theorem knowledge for this week. And the basic idea here is, first of all, let me just get this out of the way and talk about regular versus positive matrices. I'm not even going to write down the theorem. It's very simple. Because a regular transition matrix. So a transition matrix is considered positive if every single entry is positive. And in this case, that means that it's greater than 0. It can't equal 0. But a transition matrix is said to be regular if the matrix A to M is positive for some positive integer M. In other words, a matrix is regular if you can raise it to a certain number that will make it be positive. So you might look at it and it might not look positive, but if you can raise it to, if there's a number that you can raise it to that will make every entry positive, then that matrix is regular. So we're going to talk about equilibria for regular transition matrices because there is a formula. So there's exactly one distribution vector just one in distribution vector X in space N such that A times vector X is equal to X. That would be called the equilibrium distribution, also notated as this. If you see this pop up that later on, that's what that is. So all the components of this are positive, right? Because if I said we're talking about equilibria for regular transition matrices, these obviously must be positive. So if X is any distribution vector in the space N, then the limit as M approaches infinity of A to the M times vector X is going to be that equilibrium distribution. As I kind of already said, that's the limit because you keep getting it over and over or close to. It's approaching something. So another way that we can write this is that this limit is equal to a matrix where you've got the components the component column vectors being equal to the equilibrium distribution. So what we have to understand is that basically in the long run, the system will approach the equilibrium distribution regardless of the initial distribution. What they call this the globally stable equilibrium distribution. I'm going to shorten that to globally stable equilibrium distribution, GSED. So that brings us to the close of our lesson. So we're going to recap very, very quickly because we got through a lot today. So we started out by clarifying something from a couple weeks ago. And what we clarified was the problem that was in the old problem set about proving the form of the reflection matrix and proving why it's A, B, B negative A, and proving why A squared plus B squared equals 1. And what we used for that was the matrix that we were given as part of our notes for the reflection, and we kind of used that to derive that proof. We then moved on to talking about today's lesson. We started out with the basic idea of compositions of matrices, which moved us into talking about matrix products, talking about how to multiply them, their columns, sort of just the general method, the entries of the matrix product, the fact that it's non-commutative. We kind of used an example by taking reflection matrices that we already knew and setting them equal to like the names of matrices A, B, B times A, and A times B, and kind of drawing that out and showing how that works. We then moved on to talking about matrix algebra a little bit and matrix multiplication with some theorems. For example, multiplying with the identity matrix, establishing that matrix multiplication is associative but not commutative. We extended that out to the idea of block or partition matrices, where you sort of treat each block or partition as just a normal entry. And then we finally finished up with the idea of powers of transition matrices. I introduced you to this website example, the idea of a distribution vector, where you've got a vector where, you know, it's all the components have to equal up to 1, because that's sort of the point of distribution. And I kind of explained how you can use iterating matrices over and over to find an equilibrium distribution, or in other words, like sort of a limit per se, and that you have to use technology to do that. And then I finished up with a little theorem kind of recapping it. So that was what we got through today. I hope that this has been enjoyable and not too bad. And I will see you next week with, some stuff on the problem sets that I did with Dr. Prudham this week, with some notes for next week. And it should be good.